Hello, everyone. My name is Igor Halperin. I work at the Asset Management Group at Fidelity. And the topic of my presentation today will be about combining reinforcement learning and inverse reinforcement learning for asset allocation recommendations. So first, what I would like to do is to give you a crash course on reinforcement learning and inverse reinforcement learning, and then explain how asset allocation can be thought as a problem for both of them, actually. And then I will present our combined IRL and RL method and show experiments of different fund groups that we conducted with our co-workers. So the results of these presentations, this presentation are based on a couple of papers that we published with my co-workers here. So that's the main reference for this talk, and the theoretical foundations for the methods which are presented here are given in this second paper. So let me start with presenting on basics of reinforcement learning. So reinforcement learning is essentially a branch of machine learning that deals with a specific topic of optimizing actions of one agent, which is shown here, over some extended period of time, where the agent at each point in time, at each step, interacts with the environment. And at each step in time, the same sequence of exchanges of information and action happens as shown here. So first, agent gets the state of the environment encoded in some state vector S, which can be multidimensional state described in the environment. Right? And upon receiving this information, the agent acts. So it exercises actions, certain actions on the environment. And as a result of this thing, the agent receives a reward, which is a function of both these variables, the state and action. And the ultimate objective of the agent is to increase the total cumulative reward, as I will show in a little bit more details in the next slide. But things to note here is that because the agent's problem is extended over multiple time steps, and the environment is in general stochastic, then the problem of the agent involves some sort of sequential planning and forecasting over multiple time steps in the future, right? Then there is another thing which makes reinforcement learning quite different from other branches of machine learning, which is in the presence of this feedback loop. So what is the feedback loop? Feedback loop refers to the possibility that any actions by the agent can change the environment. So in principle, when the agent exercises actions, the stochastic dynamics of the environment can change for this step. And this feedback loop is unique to reinforcement learning, and it's not encountered in supervised learning or unsupervised learning. But in principle, the important point to note here is that the problem which is solved in reinforcement learning is essentially the same problem which was previously solved using classical methods of optimal control, such as Bellman-Benning problem. So this is the general formulation of reinforcement learning, and we can easily, now once we get familiar with the general formulation, we can easily map this framework onto financial applications. So we can envision an agent being a portfolio management, who interacts with the market, and all the rest of this interaction stays the same. So the state of the market will be now encoded in market prices and also in private information to the portfolio management, such as the state of their portfolio. And the actions in this case would be just trades, so buying or selling securities. All right. There is also room for the feedback effect, and this is why reinforcement learning is very well suited for these tasks. It's well known that when a large agent exercises certain trades, then it can move the market. So the feedback effect will amount just these effects. Now, there is a very interesting twist of this whole formulation, which is called inverse reinforcement learning. So why it's called inverse? Because in this setting, almost everything stays the same. So imagine that we have a historical data referring to interactions of a trader with the market. So you have historical records of market information, prices, etc., encoded in vector S, and also information about the trades made by the trader at the same time. However, what is missing in this historical data would be any information about the reward. So when you look at this data, the objective would be rather to rationalize the actions of the trader. So to explain the trading behavior of the trader by assigning to it some sort of a reward, or what is also known utility function, which would explain trading decisions of the agent. Now, very briefly, there is a math. It's a short recall of relevant math for this problem. So the variables which are included here are states, which are noted here, shown here as these blue circles. So the environment experiences a sequence of transitions between different states, which is modulated by actions of the agent, which are shown here. So the agent, at each time step, the agent exercises the action on the environment, receives a reward, and then the environment proceeds to the new state. So we have variables S, which are states, variable A, which are actions. We have transition probabilities as a part of this description. And we also have this reward function, which is the objective actually of the reinforcement learning agent, which is more specifically to maximize the total expected value of the total cumulative reward collected at each point in time here, discounted with some discount factor gamma, which is the number between 0 and 1. So the objective function of reinforcement learning is short form is shown here, and the objective of the agent would be to maximize this total expected value by finding the optimal policy, which would be a prescription of what the agent has to do as action as a function of the state, of the current state. And the policy itself can be either stochastic, so it will be either deterministic, so in this case it will be a function, or stochastic, in which case this will be a distribution, right? Now, how portfolio allocation can be seen as a problem for reinforcement learning? One approach, which we proposed in the second paper referenced above, would be as follows. We can introduce vector X as a vector of dollar values in different asset buckets, and a vector U, which will be the buy and sell decision. So both these units, both these variables are vectors of the same size and of dimension of dollars, right? So now this dynamics, what it describes what happens in the time step T plus delta T. So first, all asset positions are increased by vector U, which is the deterministic part, which is the part of the agent. And then this new asset value growth with the stochastic rate R sub T. So this is the state equation, which is a linear equation. Now, as I just mentioned, the vector X can be anything. So it could be a vector of dollar values of individual assets such as stocks in the portfolio, but for practical purposes, we need some sort of dimensional reduction. So in what we did, we used dimensional reduction by aggregation of all positions in industrial sectors. All right. Now, the next element which is needed here would be a reward. And the reward function that we proposed is shown here. It's a very simple function, which is actually quadratic function, which is very important of variables X and U. And it has the following structure. The first term is just the So all terms here are negative. So actually the reward is negative penalty. And maximizing the reward in this form is equivalent to minimizing costs. And what are those costs? The first term is just the negative cash flow, which is needed for investment at each time step. So we sum it over all assets. The second term is a mismatch between some target portfolio, which I'll specify in a second, and this new value of the asset portfolio at each time step. So we take this as an expectation. And finally, the last term would be just the transaction cost, which we modeled here as the convex function of the action variables. Now, most interesting part here is this term. So it's a penalty for a mismatch relative to a certain running goal. So, and this running goal is constructed as follows. We just take a certain index, a benchmark portfolio, for example, S&P 500, and we form a linear combination of this index with the current portfolio. So this equation is shown here. We take this index and put it with the coefficient 4, and another term which we have here will be portfolio dependent. So our running goal depends on the current portfolio. And if you count the number of variables here, you will have 4 tunable parameters. So if we knew these 4 parameters, then we would know the reward function, and we would use this reward function to optimize the portfolio. The problem is that we don't know these parameters, but to find them, we can use inverse reinforcement learning. And the paper, which is referenced in the beginning of this talk, presented a certain scheme, which is based on a combination of inverse reinforcement learning step and direct reinforcement learning. So how it looks, we take a bunch of trading trajectories for a number of funds, and we apply here a particular method. I will say a few words about how it works. It's called T-Rex. That's why you see this nice picture here, which actually takes ranking criteria for performance of individual funds and converts it into a model for the reward function. This is how we make influence of the reward function. So now once we have the reward, we can optimize the policy by maximizing this reward. So we have 2 steps in this procedure, IRL step and direct reinforcement learning step. Just a few words about the T-Rex algorithm, which we use here. T-Rex stands for trajectory ranked reward extrapolation. And this is the IRL algorithm, which was developed, presented in 2019 by researchers from Washington University. The nice thing about this algorithm is that it allows the technical implementation of these amounts to the ability of extrapolate beyond the demonstrated behavior, which is an extremely important thing. Many previous inverse reinforcement learning algorithms at most could hope for mimicking the behavior of demonstrators, but this algorithm actually goes beyond that, and it's able to improve over the demonstrated behavior, which is extremely important for financial applications, obviously, because in financial applications, we never know that the demonstrated behavior was optimal. All right. So the performance of this algorithm is illustrated in our paper, and these graphs are taken from the paper. The first thing which I wanted to show is how the algorithm converges for the IRL stage. So what we do, we take groups or a few groups of mutual funds, which are all grouped according to their benchmark indices. And for those, we use either S&P 500 or Russell 3000. And then we train on these groups. So we have few funds in each one of these groups. And for the S&P group, so the results are similar. The convergence is pretty fast actually, and for results for S&P group are shown here. So you see that all parameters seem to converge nicely to something which looks like constant values, but they're different for different funds, which can be interpreted actually financially. The differences are shown here. The next thing after we do the calibration and inference of the RL stage, we use this inferred reward function in order to optimize the policy, which would be the RL step, the step of direct reinforcement learning. And what we did to assess performance of our algorithm, we took the overall overperformance of our algorithm versus the actual performance for both train and test data set, and show them as a function of the timeline of time horizon. So we align obviously these two time intervals, which we use for training and test, are different. So we use 2 years between 2017 and 2018 for our train data set and 2019 as our test data set. But on these graphs, the time axes are aligned to show the similarities and differences between the train and test data set. And what we can see here is that we do see that our model is able to outperform the actual fund managers as a group, which is shown here. So you see that nearly everywhere these graphs are in the positive terrain, which means that we actually outperform fund managers. We also did comparison with the performance of individual funds, and you can find corresponding graphs in the paper. What we found there is that we do not outperform all of them, but we outperform most of them, at least in this backtest. So this is what we did, and in the summary, what I presented was a two-step procedure where we first use inverse reinforcement learning to infer the reward function, and then we use direct reinforcement learning to optimize asset allocation. What our model actually does, it learns from the collective intelligence of individual fund managers. And then because of this particular IRL algorithm that we use, it's able to outperform most of them. Now, the outputs of this model can be used for trade recommendations or asset allocation recommendations. And the latter can be transformed into the former. So we can use additional arguments in order to convert our recommendations at the sector level. Remember that we do dimensional reduction to the sector level. So our asset allocations are essentially recommendations of allocation at the sector level. But if we rely on some additional criteria for picking individual stocks, then we can do that as well. Right. There are also other uses of this approach. So, for example, we can use it in order to segment and classify different mutual funds according to both their declared investment philosophy, meaning what is written in prospectus and what is the benchmark, and also the perceived one via inferred parameters of its reward function. So we can use it in order to do clustering of those funds. And finally, also one other thing to note is that even though we use the particular dimension reduction method in this work, which was a reduction of exposures to sector buckets, we could also proceed in different ways and, for example, use factor-based allocation, which might be a work for the future. And on this note, I would like to end, and as extra bonus points, I would like to offer you a look at our paper, at our book, which has a number of chapters on direct and inverse reinforcement learning. And on this note, I would like to end and take questions. Thank you very much.